Hello and warm welcome to our online seminar on how to keep power reliable for the semiconductor industry. Today's session will be full of important information for electrical engineers working in the semiconductor field, especially those looking after substations and keeping things running and well maintained. I'm Sarah Esarabadi and I'm delighted to be the host of this webinar for you. I handle the vertical marketing for the semiconductor industry. And just to answer a common question we get rather often, we are recording this session and will share both the video and the slides with everyone who registered. If you have been with us before for our talks on how we power things and make them smart, we will remember the Q&A box in the top right corner of your screen. That's where you can send in your questions for our speakers, which Martin and Andreas will look at and after their presentation. Any questions we don't get to during the webinar, we will be answering by email. And remember, if you are in full screen and want to see the Q&A or chat, just hit the escape button. Before we get into the details, let's talk about the big trends the semiconductor industry has right now: sustainability, digitalization, and cybersecurity. The world is changing quickly and there's a big push to make these changes sustainable. That means lowering CO2 emissions in our production, being clear about our efforts, and making sure the public sees us in a good light. Digital tools are shaking things up, helping companies grow quickly, work smarter, become more adaptable, and stay resilient and green. Making these changes quickly and easily on a bigger scale can be tough though. In the semiconductor industry, robust cybersecurity is vital to protect the integrity of our increasingly connected world. At Siemens, we are committed to safeguard the foundation of global innovation from digital threats. Now, what does it mean for the semiconductor industry when it comes to power supply? Top of the list is the need for power that's always there. For semiconductor manufacturers, when the power stops, everything stops, and that can cost a lot. So keeping the power on is super important for all businesses. These industries still rely a lot on old energy sources, and there's a real need to switch to cleaner energy to meet global goals for a better environment. They also have to keep using less and less energy, even though making semiconductors can use a lot of it. Using data and analysis helps our clients run their energy systems and their building and production operations in a greener way. Making sure the production process is safe and the power system is well protected is a must. It keeps the people working there and the equipment safe and the business running smoothly without interruptions. And with more digital tech and the Internet of Things becoming part of how we manage energy and processes, keeping everything cyber secure is a super important topic, not just for keeping production steady, but also for how people see us. In this webinar, we are going to focus on keeping the power infrastructure safe. Low voltage switchboards have a lot to handle and can sometimes have an arc fault, which is rare, but a big problem. We will dive into why these happen, what they can do, and how the usual safeguard stands up. All this to keep people and property safe and cut down on any shutdown times and costs. Here is our plan for the webinar. We will talk about arc faults in low voltage switchboards, what causes them, and what comes next. We will share knowledge from the International Electrotechnical Commission, IEC, on this issue. We will look at ways to stop arc faults from happening, including safety steps you can take before, during, and after they might occur. We will show you how having an active arc fault protection system can help. And we will tackle some common questions. Martin and Andreas, we are ready to hear what you have to share with us about keeping power supply safe and outsmarting arc fault. Over to you.
Welcome to our webinar, Sivacon S8+, arc fault protection in low voltage switchboards. My name is Martin Sichting. I'm responsible for the Sivacon S8+ in the region Germany. Together with me in the studio, I'm supported by my colleague Andreas.
I would also like to welcome you to today's webinar. My name is Andreas Stöcker, and I'm responsible for the product management for Sivacon S8 low voltage switchboard.
Andreas, low voltage switchboard is produced in accordance with IEC 61439-2. This regulates, for example, the topic of degree of protection, internal separation, and the design verification, but also the subject of arc fault protection.
The standard defines the requirements for the construction and behavior of the switchboard. However, the behavior in the event of an arc fault is explicitly not covered by this. The requirements for the behavior under condition of arcing are regulated in a technical report, which is not part of the IEC 61439-2. But before we go deeper here, we should perhaps first look at what an arc fault is and what can lead to this worst-case scenario. According to the definition in the standard, an arc fault is a short circuit burning freely in air that can occur as a result of a fault between active parts of different potentials and or between active parts and other conductive parts within a switchgear assembly. This ionizes the air and makes it conductive, allowing the current to flow more or less unhindered in the resulting plasma. The pressure rises rapidly, like an explosion. There's a bang. As a result, the temperature also rises sharply and can reach values of several thousand Kelvin. In addition, the high temperature also burn or vaporize the material surrounding the arc fault. The first thing that burns is the insulation materials of the cables. Next, the copper, and after some 200 milliseconds, the steel of the enclosure can also start to burn. The burning materials may also produce toxic fumes that should not be inhaled under any circumstances. All in all, this is a very dangerous event, which can ultimately lead to serious, possibly even fatal, injuries to people and, of course, damage of electrical facilities. In this short video, you can clearly see the destruction that comes from such an event.
That's very impressive. It is also important to know how such incidents can occur. First of all, arc faults are very rare. They represent an absolutely exceptional situation. In practice, however, we see a wide range of possibilities as the cause of arc faults. On the one hand, these can be, for example, external circumstances such as pollution, which means that the insulation properties in the switchboard are no longer guaranteed. This can be, for example, also by animals that can enter the system and cause a short circuit. However, handling errors are also a possible source of risk. For example, incorrectly carried out maintenance work or non-compliance with the environmental conditions for which the system is designed. Like in this example, a system that stood in a building without windows and heating and is iced over. Last but not least, errors in planning also pose a further risk, for example, due to incorrect dimensioning of equipment or cables. In an extreme case, this can lead to an overload of the components, which can then lead to failure and also to short circuit. And this means an arc fault.
And if this risk actually occurs, then the consequences are drastic, as I said in the beginning. The danger to life and limb is definitely the worst aspect. But of course, there are also economic consequences due to the destruction of the system and thus the outage of the power distribution. This means nothing other than a system shutdown and thus loss of production. The costs for this quickly go into the six-figure range and above. Considering that in the event of an outage, the repair work can take longer, days or even weeks. I don't want to go into the possible consequences of personal injury here. A technical report from the IEC standard series is helping us. IEC Technical Report 61641 describes the requirements for testing low-voltage switchboards under the condition of arcing. Technical report means that it is not a standard. It's an informative document that reflects the state of the standardization and can be incorporated into a standardization work later. No measures are defined how to achieve arc fault protection. This is left to the manufacturer. However, it defines how the test is to be carried out and how the test result is to be evaluated. These include voltage, currents, and the burning time of the arc, but also features such as who has access to the assembly. Everyone, that means unrestricted access, or only authorized personnel. This corresponds to restricted access.
The proof of arc fault protection can be carried out in two different ways. On the one hand, by testing. In this case, there's an arc tested zone. And on the other hand, by taking appropriate measures that make the occurrence of an arc fault unlikely. Here, we are talking about an arc protected zone. This can be achieved, for example, by insulating conductors. In a switchboard, you will usually find a combination of both. Arc fault tested and arc fault protected zones. It is also important to define the protection goals in advance.
Here, the minimum requirement would be personal protection. This means that a person standing in front of the system will not be harmed. In addition, system protection can also be achieved. And this is important for avoiding or reducing downtime. The effects of the arc fault are then limited to a defined part of the system. For example, a defined part can be a cubicle of the switchboard. This would then have to be replaced after the event. Or you can narrow down the area further to one compartment. In this case, only the compartment with the withdrawable unit would have to be replaced in a system in withdrawable design.
After the tests, it's time to evaluate the test results. When is a test passed?
Perhaps first a few words about the test arrangement. There's a grid standing in front of the test specimen. Attached to this grid are small rectangles of fabric, so-called indicators. These indicators are intended to simulate the clothing of a person standing in short distance, approximately 30 centimeters, in front of the system. Two different fabric qualities can be used. A lightweight cotton fabric designed to replicate unrestricted access, like in leisure wear, or a heavy fabric of around 150 grams per square meter that represents the work clothes of staff with limited access.
There are a total of 7 criteria for passing the test. For this purpose, the test result is evaluated based on these criteria. The first 5 criteria are required for personal protection, the remaining 2 criteria for system or assembly protection. Criterion 1 means properly secured doors, covers, do not open and remain in position in such a way that they provide a minimum degree of protection IP1X. Criterion 2 states that no parts of the switchgear assembly with a mass of more than 60 grams are thrown away. In order to meet Criterion 3, up to a height of 2 meters, there are no holes as a result of burning of the arc fault on the outer enclosure parts that are designated as freely accessible. For Criterion 4, the indicators don't ignite. And in the case of Criterion 5, the protective conductor circuit for accessible parts of the enclosure is still effective in accordance with the IEC 61439-2 standard.
If all this is fulfilled, then we have achieved personal protection. If the following criteria 6 and 7 are met, the protection for the assembly is proven. Criterion 6 means that the arc fault is confined to the defined area of the switchgear assembly where it originated and does not propagate into adjacent areas within the switchgear assembly. With criterion 7, emergency operation of the remaining switchgear assembly is possible after fault elimination or after disconnection or removal of the affected functional units in the defined area.
In order to be able to describe the whole thing more easily, four so-called arcing classes are defined in the technical report. We start with the arcing class A. Here, we achieve personal protection under arcing conditions by fulfilling criteria 1 to 5.
Arcing class B corresponds to a switchgear assembly with personal and system protection under arc fault conditions that meet criteria 1 to 6. In other words, limit the impact to a certain area. In arcing class C, limited operation as described in criterion 7 is also possible. Last but not least, there is arcing class I. This is a switchgear assembly with a reduced risk of arc faults due to the sole use of arc-protected zones, meaning insulation, for example. In practice, however, this form will occur rather rarely. A system that is completely protected by insulation is difficult and labor-intensive to realize.
In the next part of our webinar, we want to show you how we, as a switchboard manufacturer, can meet these requirements and help you plan and install a safe power distribution. The protection of your personnel and equipment starts with the planning stage. With the Semaris suite, you have good and integrated tools at your disposal. In addition to Semaris Project as a planning tool, Semaris Curves as a visualization of the time current characteristic curves, and thus the trip characteristic curves, we offer Semaris Design. This allows you to simulate your grid setup and use the results to design your switchboard and protection devices to meet the requirements. These are general system design data, for example, rated current of the main busbar and the rated short-term withstand current ICW, the switching capacity of the incoming circuit breaker or outgoing breaker ICU, or the expected short circuit current and the arcing time IP arc and T arc.
However, the construction of the switchboard itself also supports the preventive measures. Passive measures here would include a uniform operating concept for all withdrawable unit sizes, various locking devices for main switching devices, and mechanical locks that allow switching only when the withdrawable unit is correctly inserted and when the door is closed. Other measures are the insulation of the main busbar and the customer connection, the right selection of internal separation, the use of shutters at the distribution busbars or adapter plates or on the circuit breaker. These can prevent live parts from being accidentally touched with a tool during maintenance work. Further ones includes, for example, the use of coding. This avoids confusion between withdrawable units of different ratings and circuit breakers of different ratings.
Reactive measures include, for example, the arc-resistant hinge and locking system, as well as protective measures at the front ventilation openings, along with pressure relief flaps in roof plates. Furthermore, the use of the arc barrier, which prevents the arc from moving from one cubicle to the next, is a simple and efficient means of limiting an arc fault to one cubicle. But is that all enough?
As always, it depends on what is to be achieved. However, the requirements of IEC Technical Report 61641 can be met in any case. This still looks spectacular in the high-speed recording, but this is a past test with the classic upgrade measures.
In the last section, we discussed how we can use passive and preventive measures to limit or even avoid an arc fault. However, when limiting the arc fault with the help of passive measures, an arc flash burning time of 300 milliseconds can be expected. This duration in an event such as an arc fault also means a very high energy conversion. Let's recall the graph on the thermal influence that we presented to you at the beginning of the webinar. We see that there is an increased risk of fire beginning in the range of temperature rise from approximately 100 milliseconds. Due to the exponential increase, the risk of damage is increasing with every millisecond. In the following, we would like to introduce you to a way to further reduce the tripping time and thus the energy released.
In this case, we are talking about an active arc fault protection through an internal arc fault mitigation system, which is integrated according to IEC Technical Specification 63107. Such a system usually consists of a detection relay, light sensors, current transformers, a circuit breaker, and an optional quenching device. More on that in a moment. The light sensors are installed in different areas of the switchboard and monitor for the occurrence of light emission from an arc fault. If a light event is detected, a signal is sent to the detection relay. This sends a trip signal to the circuit breaker of the incoming feeder. It opens and the arc extinguishes. In order to avoid false triggering by other bright events, the sensors are precisely matched to the spectrum of an arc fault. And the sensors are also available with different light sensitivities, depending on where the sensor is to be installed.
A further safeguard is the use of current transformers in the incoming feeder as an additional triggering criterion. Only if a steep rise in the current is detected in addition to the light signal, the trip signal is sent to the circuit breaker. All of this happens very fast, within about 15 milliseconds until the circuit breaker has switched off. This means that the impact on the system is significantly reduced. In order to ensure protection, even in the event of an arc fault occurring on the primary side, in which case the CTs would not measure a current flow, there is also a special pressure sensor that trips the upstream distribution in medium or low voltage.
To be able to reduce the stress even further, I would like to remind you once again of the pressure curve. This system can also be combined with a quenching device. This reacts so quickly that you can get ahead of the peak of the pressure curve and can thus also reduce the mechanical load on the system. What does the quenching device do? Well, the device causes an all-pole short circuit on the main bus bar. This short circuit immediately removes the energy from the arc fault and the arc goes out. The resulting short circuit is now switched off by the circuit breaker.
How does the quenching device work? The setup is quite simple. Inside the device is a cylindrical contact which is moved extremely fast when triggered by the magnetic field of the coil and thus creates a short circuit. How quickly does the system respond? The total triggering time from the ignition of the arc fault to its extinguishing is usually significantly less than 5 milliseconds. If we remember the pressure curve, we prevent the pressure wave from becoming so strong in the first place and causing any major damage.
In this video, you can see a test with the quenching device activated. The impact on the switchboard is now significantly reduced.
And since the quenching device is a purely electromechanical principle, there's another great advantage. After tripping and, of course, eliminating the cause of the malfunction, the system can be easily reset and is ready for use again within a few minutes. This means that no components need to be exchanged or replaced. A simple reset is all it takes to restore the system arc fault protection. In addition, a test function is possible with the system, which can be used up to 100 times. And since the quenching device is a purely electromechanical principle, there's another great advantage. After tripping and, of course, eliminating the cause of the malfunction, the system can be easily reset and is ready for use again within a few minutes. This means that no components need to be exchanged or replaced. A simple reset is all it takes to restore the system's arc fault protection. In addition, a test function is possible with the system, which can be used up to 100 times. And as the system can be used up to 690 volts, 100 kA, it can be installed in the majority of applications. This ensures comprehensive protection of the system-related processes, and the personnel. The three essential components of an arc fault, light, current rise, and pressure, are detected and evaluated. A shutdown takes place quickly and safely.
Let's summarize. An arc fault is the worst possible event that can occur in a switchboard, although it is extremely rare. In the case of an arc fault, large amounts of energy are converted within a very short time in the form of an increase in temperature and an explosive increase in pressure. IEC 61439-2 defines the basic specifications with regard to the requirements for switchgear design verifications, but not for arc fault protection. IEC Technical Report 61641 defines arc protected and arc tested zones. The technical specification 63107 describes the integration of active arc fault protection systems. A distinction is made between arcing class A, personal protection, class B, personal protection and assembly protection, and class C, personal protection and specific assembly protection, including emergency operation after an incident.
An arc fault is inevitably accompanied by an outage of the system as well as downstream processes. The resulting downtime costs can quickly reach a financially sensitive area, leading to further additional costs. Therefore, it is important to avoid arc faults and their consequential costs, or to minimize them as much as possible. In order to limit or even avoid the arc fault, preventive, passive, and active options are offered. At the same time, active arc fault protection currently offers the best possible protection for people and systems. With the help of sensors, the three decisive properties of an arc fault, light, current increase, and pressure, are detected. With the help of an internal arc fault control device, IACD, the upstream circuit breaker can be switched off after the sensors have tripped. The shutdown time is reduced to less than 50 milliseconds. If the quenching device is also used, the arc fault can be cleared in less than 5 milliseconds by a short circuit of the main bus bar. This further reduces the stress on the system and further minimizes the impact.
If you want to read more information on this topic, we recommend our white paper, Arc Fault Prevention and Protection, which is also offered in the information package for this event.
We believe that our webinar has given you a better understanding of the topic of arc fault protection. If you have any further questions, please do not hesitate to contact us.
We would like to use the remaining time for a Q&A session. First question is, in your design, is arc allowed to travel? If so, then how safe is it to work on other feeders? Depending on the arcing class, the arc may also travel in the system. Generally, tests as per IEC 61641 are carried out with doors closed. Arcing class C, with a limitation of the effects of the arc to a defined area, will reduce the effects of the arc. And measures like arcing barriers or additional insulation will prevent the arc from traveling. Combination with the active arc fault protection will reduce the energy conversion further significantly. Tests in line with the IEC with open doors have been passed with these measures. Next question. Does the system use protective core transformers or normal transformers to measure the current? The system works with normal transformers, as not the absolute value of the current is required, but the rate of change.
Next question. I see in your example the arc fault device is detecting the light. Is it possible to trip the system using a flashlight? A flashlight can be used to trigger the system if the flashlight is very close to the sensor. This can be useful for testing during commissionings, for instance. However, to avoid false trips, it is important to not only rely on light and to combine it with a current signal, or in case if the in-camera section with light and pressure sensors. The next one. In what specific industry do you recommend the use of AQD? Any application or industry that is relying on the highly availability of their low voltage power distribution can reduce this risk with the implementation of active arc fault protection. For example, process industry, but also data center applications. Next question. At what point in terms of Ka and milliseconds should I consider arc protection? This is not so much a question of rating as of what the consequences of a loss of power supply could cause. The damage to the system may be not as drastic in a range of only a few Ka, like below 10 or 20 Ka. Regarding personal protection, this question should be answered with, it is always necessary. The next one. I'm having an application in the marine sector. Is this more likely for arc flashing due to vibrations? I'm not aware of a higher arcing risk in marine applications. Nevertheless, availability is highly important here. An active arc fault protection system can reduce the downtime if an arc fault would occur. The next one is, can the AQD be retrofitted in any type of low voltage boards of any make? We offer this system only as a solution for our Sivacon SA+ switchboards.
The next question is, what is the most common cause for arc fault? From the statistics, we can see that the common causes for arc faults are relatively evenly distributed. However, the most common cause is actually handling errors by the personnel. And the next question, what are the effects if no arc fault protection is used in a locally manufactured panel? If an arc fault occurs in a system that is not designed to withstand its effects, it may result in the complete damage of the system, maybe even fire in the surrounding location. And if people are involved in such an incident, the consequences can actually be fatal.
Next question. Is the AQD always tripped with an arc fault, or is there any cases when the arc is not so powerful and just need to be tripped by the circuit breaker? If light and current rise are present, the AQD will be tripped. A weak arc, for instance a serial arc fault, will eventually also become a parallel arc fault and therefore must be prevented fast before it evolves.
How many sensors the relay can handle? The main relay can handle up to 12 sensors. If that's not sufficient for the application, expansion units can be added. Each of this can handle additional 12 sensors. After all, the system is normally completely designed and set up by Siemens, so that the planner or operator does not need to take care of that. Next question. Can the arc fault be localized with the help of the active arc fault protection? Information which sensor has tripped is indicated on the front of the relay. Next question. What would be the commercial implication to incorporate the arc fault protection system? The costs are highly dependent on the system size and configuration. You have to consider between 10 to 15% of the system price.
Can you show the location of the AQD and how it is connected to bus? The AQD should always be mounted as close as possible to the incomer to reduce stress on the system if tripped. The device is directly connected to the main bus bar. How our optical sensors are placed in Form 4B installation. Sensors are placed in relevant locations. In a 4B installation, this includes bus bar compartment and vertical buses. Next one. What precautions should be taken when installing light sensors in an IP31 enclosure, as it is less protected from outside dust? The sensors are placed in such a way that they are not affected by dust. For example, facing sidewards or downwards. The next one. Are all the modules provided with light and pressure sensors? Light sensors are only installed in relevant locations of the assembly. The installation in withdrawable units is not necessary. Combined light and pressure sensors are only installed on the incoming side of the incomer. The next question. Is arc fault protection possible on small withdrawable units? Arc fault protection is available for all withdrawable modules. As mentioned, a system always combines different measures to accomplish protection. No sensor is needed in the installation of withdrawable units. Protection is achieved secondary side with the current limiting protection device and primary side with insulation. The contacts and vertical distribution bus are protected with sensors.
Next question, can you please explain short-circuiting the main bus with the AQD and what medium is used for arc quenching? The AQD consists of a cylindrical contact that is moved in air by the magnetic field of a large coil surrounding it, a Thomson coil. It is mounted directly to the main bus, thus this contact creates an all-pole short circuit to the main bus bar. And are absorbers necessary? No. The energy levels in low voltage are too low so that no absorbers are necessary. Is there an interlock in the panel for tripping upstream during arc fault in panel? There is no interlock required to the upstream breaker. If the arc occurs secondary side of the incoming breaker, it will be tripped instantaneously. The upstream breaker will remain closed. If the arc occurs on the primary side of the incomer, the upstream breaker will be tripped instantaneously by the system.
Next question. What if paralleling the AQD with multiple bus bar connected by sectional switches or bus ties? Specific arcing schemes are available to consider such designs. Each section needs to be equipped with its own AQD. Depending on the state of the bus ties and incomers, the required AQD and breakers will be tripped. Next question. Can the parameters of the AQD or ICD be adjusted over the operating time of the switchboards, for example, system expansion? Initially, the system is pre-configured at the delivery. If adjustments or changes become necessary, this is possible.
Next question is the AQD always required, or can the IACD also be used on its own? The IACD can be used on its own. It would then trigger the incoming ACB directly. What is the time the system shuts down in case of only using IACD or arc fault detection? Only using the detection without the quenching device, the tripping time is approximately 50 milliseconds. Using the AQD reduces the tripping time below 5 milliseconds. And in the graph, you can see why this is important. Using a combination of IACD and AQD gets you even ahead of the pressure peak. And this really minimizes the mechanical stress on the system. Next question. Is it possible to measure the intensity of the arc with this device and the total duration of the quenching time? The tripping current could actually be read from the incoming ACB, from the ETU of the ACB. The tripping time is not available. Next question. What is the max value of arc current the quenching device can successfully clear? The system is rated up to 100 kiloamps at a voltage of 690 volts. Next question. Is the overcurrent relay enough to isolate the system before such scenarios? The overcurrent relay or the electronic tripping unit of the ACB is only sufficient with other mechanical measures that strengthen the system. Next question. Is there any option to select only one sensor type? Pressure, current, or light? Yes, the system could be configured to react on light only. However, this could lead to false trips due to switching arcs or other strong light emissions imposed on a sensor. So therefore, it is always recommended to combine light and current signals.
Do you put on instruments on doors, for example, ammeters, relays or something, in tests? This is a very important topic. Usually, switchboards are equipped with multiple devices or instruments on the doors. And it should also be ensured that these devices do not fly away from the board as defined in Criterion 2 of the IEC Technical Report 61641. Our tests have also included typical door-mounted devices such as ammeters, IR monitoring windows, relays and such. These tests have been passed.
And the next one is, does the AQD also ground the bus bars? No, the AQD creates an all-pole or a three-phase short circuit on the main bus bar. Next question. Can the system indicate to other protective IEDs, intelligent electronic devices? The system has a relay interface to signal to other systems or such IEDs. That way, it can also be integrated into other systems. Next question. After 2 full load uses, what needs to be updated to allow full use of the switchgear? The system is designed to withstand 2 full load operations. After a second arc fault incident in the same assembly, the AQD needs to be replaced. But keep in mind that this must be a very, very rare incident at all. Next question. Is there a let-through characteristic available for the active arc fault protection? No, this is not available. The AQD creates an all-pole or three-phase short circuit on the main bus. This means that the full short circuit current will be loaded on the system until the ACB is tripped. But this is what the system's ICW is designed for. So this is not an issue.
Next question. I would like to know the difference between arcing class B and arcing class C with an example. The difference between class B and C is that class C provides so-called emergency operations after removing the affected part of the assembly. The assembly must be designed in a way that an affected part can be removed. So the design must be in some way modular. For example, withdrawable design where the affected unit would be removed and the rest is still working. Or an ACB section that, if affected, would be removed from the assembly. The next question. Is this a part of type-tested panels? The switchboard is tested according to IEC 61439-2. The current term would be design verification instead of type test, but it basically means the same. The arcing tests are carried out according to IEC Technical Report 61641. Next question. Does the IEC ask for arc protection as a mandatory means for low voltage switchboards, or it is up to customer needs? Currently, arc fault protection is not a part of the IEC 61439, so it needs to be agreed between customer and manufacturer separately.
And with that, we have come to the last question. Has Sivacon been tested for arcing class I, and how is that different from class C? Class I cannot be tested. Class I requires an assembly to be insulated so that no arc can be ignited. That insulation needs to provide an IP degree of protection IP4X so that no live parts are accessible. Parts of Sivacon S8 are realized in class I, however not the complete system. This is also a question of economy, as insulation requires significant additional effort. Sivacon S8 as a complete system is available up to class C, meaning that the design consists of tested and insulated zones.
Thank you everyone for asking your questions, and thanks to Martin and Andreas for their answers. If we didn't get to your question, we will follow up through email. And if you think of something later on, feel free to reach out to our team. They will get back to you quickly. You will find the Sivacon S8 brochure, our arc fault protection guide, and the webinar slides ready for download in the top right corner. Remember, if you're full screen, you will need to press Escape to see them. You will get access to the recording of this session right after we wrap up, using the same link you used for this live event. It was great having you all actively participating. I hope this session on Sivacon S8 Plus arc fault protection was helpful. We covered the start and impact of arc faults in low voltage switchboards, insights from the IEC, how to prevent arc faults from happening. Looking forward to our next webinar together. Stay safe, take good care, and see you next time.